So today we talk about lubricant foaming simulation, how Particleworks can predict lubricant foaming in different kind of conditions and for different designs of gearboxes, engines, oil sump, and other kinds of application. This is Massimo Galbiati from Particleworks Europe. The slides were prepared together with Michele Merelli, who was not able to attend today. And this is the agenda of the webinar. Um, we'll have a short introduction to meshless CFD Particleworks, just to give you an overview of what the software can do, what's available in the software, and why meshless CFD is applied in powertrain simulation. We talk mainly about powertrain, but there are other applications, obviously, where meshless CFD can be applied. Then we dive into the foaming theory, or let's say in the practical effects of foaming on the performance of gearboxes and engines and pumps. And then we will use some demo cases to show you how the foaming aeration model available in Particleworks can be used to support and to help the design of gearboxes, engines, tanks, and pumps to minimize the effects of foaming. At the end, we will also talk a little bit about lubricants formulation, so not related to the hardware, the gear design, so the engine design or the pump design, but we will talk about a specific use case coming from Total Energy, that is a lubricant manufacturer, because we started a collaboration with Total, and I will show you some preliminary results of an activity we have actually concluded recently. And then the rest of the full paper, the full presentation of this cooperation with Total will be soon available and will be presented in our conference in October. Let's start from an introduction to Particleworks and meshless CFD. Particleworks is a meshless Navier-Stokes solver. Meshless in this case means that the fluid is discretized by particles instead of computational cells. So instead of using the classical grid that you probably know from finite volume CFD, we use particles. And each particle is representing a certain volume of fluid. The software can simulate single phase and multi-phase flow. Single phase means, for example, that we can simulate only the oil or lubricant or liquid phase in a gearbox, in a transmission system, in an electric motor, or for piston cooling, for example, you see here. We can also add the effect of air or gas flow on the liquid phase by multi-phase simulation. So the software can simulate multi-phase, and it can also calculate temperature, both in fluids, so oil and gas, but also in solid bodies. So for example, we can run a conjugate heat transfer simulation of the piston or of the windings and rotor of an electric motor. So Particleworks is not only meshless CFD, but it's also heat conduction and multi-phase flow. Here you see an example of temperature prediction in the lubricant of a gearbox. You see the temperature evolving, so we can apply power sources associated to the gears, to the meshing of the gears, to the bearings. We can include the heating effect due to shear heating, and this produces heating of the oil, of the lubricant, but also we can calculate in the same simulation with the same model the temperature of all the components of the gearbox, including the heat transfer between the solid bodies and the and the oil or gas phase, and the heat dissipation to the external environment on the external surfaces of the housing. The method on which Particleworks is based is called moving particle simulation. You are probably aware that there are different methods available. One of them is SPH. MPS, moving particle simulation, is quite similar to SPH, but not exactly the same for a number of, let's say, mathematical reasons. The moving particle simulation was originally proposed by Professor Koshizuka from the University of Tokyo, and together with other people from the Japanese University of Tokyo, Professor Koshizuka co-founded almost 20 years ago Prometech Software. Prometech Software is the company that develops the software Particleworks, and as you probably know, Particleworks Europe is the European office of Prometech. Here is a parallel between the Eulerian approach that is typically applied by finite volume method, so classical CFD, standard CFD based on an Eulerian approach. Let's say the drawback of the Eulerian approach, the mesh-based approach, is that first of all you have to generate the mesh, and this could be time-consuming and demanding depending on the geometrical complexity of the system. It becomes quite demanding and quite complex when you have moving parts. That's why mesh-based CFD is quite difficult to apply to powertrain systems, to engines, gearboxes, clutches, electric motors, when you have free surface flow with high deformation of the free surface, and at the same time you have moving parts. This would require complex management of moving mesh or other methods to deal with the motion and deformation of the mesh. So that's why meshless methods started to be developed by Professor Koshizuka and the University of Tokyo to try to simplify and to speed up the simulation process for powertrain applications. To show you a comparison and where the benefit is of using Particleworks and meshless CFD, here is a parallel between finite volume CFD and moving particle simulation. The two first steps of the simulation process, so the CAD cleanup, the fluid volume extraction, and the meshing part, are not needed for the moving particle simulation method in Particleworks. What Particleworks does is to read the CAD, the 3D CAD, the solid bodies of the CAD, so the gears, the pistons, the casing, or the other components. So the CAD as is, you need to set up the fluid boundary conditions, fluid properties and boundary conditions, numerical settings, and then you start the simulation. So one big benefit is that you don't need to carry out these two steps. So this is a huge amount of time and man hours saved at the beginning of the process. And the second benefit is related to the GPU and multi-GPU capabilities of Particleworks. Particleworks was originally conceived to run on GPUs, and this makes the simulation extremely fast and also affordable, even without huge HPC clusters. To start talking about aeration, aeration is a specific model available in Particleworks. Here you see some examples. We will talk today about aeration of oil, lubricants in general, for the two first topics that you see here. So air suction in engines, mainly related to problems for the sump and engine pump. And the second topic is, it will be actually the first one, the most important one, is foam generation and foam foaming in gearbox lubrication. The same kind of model uh, could be applied to other types of foaming processes, like, for example, for food. In this case, you see foam generation in a coffee cup, but it's obviously not the topic for today. So after this brief introduction about Particleworks and meshless CFD, I will give an introduction about foaming lubrication, the drawbacks, the problems generated by foam, and then we will go into the examples and some industrial use case, or at least some use cases that we built using demo models. So where does foam come from? Foam is actually already there. Air is already in every kind of liquid, water, lubricants, any kind of material contains air. Some estimates is that lubricants naturally contains from 6 to 12% air in volume. This is obviously not visible depending on the conditions, depending on pressure and temperature, the rate could change. And the problems start when the air is either released or when more air is entrained into the lubricant. Let's say that air can come out of solution, so it's originally dissolved, and it comes out due to pressure drops at high speed. This is basically phenomena associated to cavitation, high speed, and high pressure drops that might happen at pumps, flow restriction, bearings in general when you have rotating parts at high speed. We will not talk about this kind of phenomena. What we will talk about is the second phenomena that you see here, that is related to high shear agitation, air entrainment associated to the splash, the effect of churning and the effect of rotating parts and moving parts on the free surface of the lubricant. In addition, in addition to air, oil and lubricants also contain other kinds of contaminants, let's say. It can be water, it can be solid, it can be solid particles, or other kinds of fluids that can degrade the oil and can stabilize over time the foam, the air bubbles in the lubricant. So there are different kinds of phenomena associated to the presence of foam. We will focus on let's say, the mechanical effects that can produce foaming, that can entrain air into the lubricant and then produce foaming. To give you an idea of the costs of foaming, we mention here some of the problems related to the foaming effects. Oil aeration can produce a reduction in the hydraulic efficiency of pumps. It is estimated that a 2% air volume can produce a reduction up to 12% in the flow rate of a pump. Reduction of heat transfer, so cooling efficiency. Test with the mechanically aerated oil shows that the heat transfer coefficient can reduce by 50% up to 50% with respect to degassed oil, so clean oil. Obviously, gearbox losses, power losses associated to the oil splash. This is obviously one part of the losses of the gearbox, but the comparison between clean oil and oil with foam shows a difference of up to 30% due to the foam, and the same can be shown for bearings. So the aeration of oil and lubricants can increase by 5% the total losses of bearings and similar systems due to aeration. And finally, this is a chemical process, oxidation. The air, the oxygen inside the air can produce oxidation and degradation of the lubricant quality over time. So faster oxidation of the fluid. These are some of the problems. And this is what Particleworks can do. Obviously, Particleworks cannot simulate all the phenomena I mentioned. It cannot simulate any chemical phenomena. What Particleworks can do is to simulate physical, mechanical phenomena associated to the uh, oil-air interaction, to the oil air entrainment by the oil due to mainly two phenomena. The first one is the bubble generation by the interaction of the lubricant-free surface with moving parts. So when a gear rotates and brakes, the oil-free surface it entrains air and bubbles are generated. Bubbles are entrained, generated, and then they follow a certain path and lifetime. The second kind of phenomena that can be simulated by Particleworks, by CFD, is the bubble generation by liquid-liquid interaction. So when the free surfaces interacts with falling droplets with oil jet, again, the phenomena is similar to the first one. There is air entrainment and bubble generation. So the aeration model available in Particleworks include these two phenomena, and the outputs from the simulation are the amount of foam inside the lubricant, the growth rate of foaming as a sort of ramp up, and then it tends to stabilize to a certain air volume fraction in the oil. The software can estimate the growth rate and the final volume fraction, transportation, bubble transportation, extinction. So when droplets become too large, and typically when they reach the free surface due to free surface and surface tension effects, there can be extinction of bubbles, coalescence. This is another typical phenomena that is solved by the model. Lifetime, so we can estimate the how long bubbles survive depending on their diameter. And one of the main output is the bubble size distribution. The bubble size distribution shows how big and the frequency of the particle size of the droplets, of the bubble size inside the lubricant. The aeration model that is available in Particleworks was developed by Prometech together with Honda. There's a public interview available to the Honda R&D engineers showing how the development and the cooperation between Honda and Prometech worked. What they basically did was to start from a problem from Honda related to the excess of bubbles in an engine, and using real life data and experimental data from Honda, Prometech developed a model that was able to predict the foam generation, bubble size distribution, and this kind of model was validated against the available experimental data. The final aim of this model was to have a model that could be used practically in everyday engineering design life to optimize the hardware, to optimize the engine channels, the sump depth, the gear shield, or other kinds of devices to minimize foaming without using physical prototype. So the aim, as usually, is to reduce the number and the cost associated to prototypes and physical testing, and substitute physical testing with simulation and virtual testing. The model was developed. Now, I don't want to enter into the details, but just to give you an idea of how the model was developed and validated. The engine was a clear case was built. Using this clear engine, it was possible to visualize and measure by means of high-speed camera the foaming level, the bubble size distribution in different parts of the engine, and using different kinds of layouts to extract the lubricant and to measure the foam level and foam bubble size distribution after some time. So there was the original engine, there was a gutter to extract part of the oil, and then there was a separate tank to let the foam stabilize and to measure the amount of foam and its distribution. Here you see some details from the findings mainly related to the different areas and to the bubble size in the different areas. So it was possible to understand that the peak density of the bubble size spectrum was at 0.5 millimeter. It was possible to identify fine bubbles with a particle size lower than 0.3 millimeters everywhere in the circuit, in the oil circulation circuit. And it was also possible to identify, let's say, the maximum bubble size in the range of 2 millimeters. So no bubbles with a diameter higher than 2 millimeters could enter the pump. And here you see visual comparison between experimental data and simulation from Particleworks, where you see the particle size in the range of 1 millimeter, bubble size in the range of 1 millimeter. The validation was done not only on the amount of oil, but also, as I said, on the bubble diameter. So this is the, let's say, the lifetime, and this is the bubble diameter. And you see, for example, that there are no bubbles with a diameter higher than 2 millimeter, and you sort of see the particle size distribution or bubble size distribution in comparison with the lifetime of the bubbles, where you see a peak around 1 millimeter. So this means that, for example, the software can predict both the distribution and how long the bubbles will survive in the system. Other kinds of validation done by Honda and Prometech were related to the transport phenomena. Transport phenomena and again lifetime. Here you see a comparison. This is a simple tank with a lateral pipe where bubbles are injected, and the validation was done by comparing the trajectory of the air bubbles and also the diameter again of the air bubbles. The bubbles are injected with a certain fixed diameter, and then the diameter evolves according to the physical phenomena, coalescence, extinction, that can be calculated by the software. And again, here you see a validation of the simulation model, again, in terms of traveling distance, horizontal distance from the pipe with respect to the bubble diameter. And you can notice that the red points that are the calculation results are in the same cloud of points coming from the experimental measurements. So after validating the model has been applied to real designs of the engine to design the engine so that the foaming amount could be minimized. I um, I want to give you some examples related to a gearbox, again to show what the software can do in terms of geometry comparison. When it comes to foaming, foaming is, as we said, related both to physical phenomena, air entrainment due to mechanical effects, but is also related to chemical phenomena. In this example, what we did was to simulate a specific type of lubricant. So let's say we keep the physical properties and the chemical properties of the oil as given. We don't want to compare different lubricants. We just want to compare different designs, different operating conditions of gears. The gearbox is obviously not a real one. It's a very simple one. We cannot show real data. We have some at the end. But the idea is that in this example, we compare different rotational speed and different directions. The gears are rotating in the same direction in these two cases on the right-hand side, and are rotating in opposite direction on the left and top of this video. Here you see in pink, these are the air bubbles. We don't show the oil, otherwise anything will be visible. First of all, you can notice that there is no air at the beginning, so the system is initialized with pure oil. There is no air in the system. Bubbles are generated by the gear interaction with the lubricant. You see different amount of oil, different amount of bubbles. This is shown in these two charts. You see the air volume fraction. This is a comparison of the different conditions and different designs or different rotational directions. You can notice that the amount of air entrained and the history, how the growth rate of the foaming is different depending on the speed and depending on the direction of rotation. And after a certain period of time, we can also evaluate the total. In this case, we are showing the total number of air bubbles. This can be translated into air volume or air volume fraction as shown above. Uh, Obviously, the particle size can affect the translation of the total air bubbles in terms of numbers into the volume fraction. So both effects, number of particles, number of bubbles, and particle size distribution are accounted for. And here you see the same. So we can have a visual comparison of the air generation. We can detect where the foam is generated. We can calculate the bubble transportations to understand where the foam goes and where the oil is more, let's say, contaminated by the foam. This is a top view of the same example. So, for example, you see that at higher speed, you can visually already see that there is a higher amount of air entrained, and so higher oil foaming. And it seems that when the two gears rotate in the same direction, again, you have a higher amount of foam generated. Now, the message from this first example, that was a very simple example because we cannot show a real gearbox simulation, is that the software can predict and compare different designs of different operating conditions. The software can also compare different lubricants. In order to compare different lubricants, obviously, we have to account in some way for the chemical properties of the lubricant. This cannot be done by CFD in general, because when you define a fluid in CFD, what you define, what you give is the density, the thermal properties, the surface tension coefficient, viscosity, and contact angle. So you don't have any input related to the presence of specific chemicals to reduce foaming or other kinds of chemical properties. So what we have done and what we investigated was done together with Total Energy, that is a well-known oil and gas and lubricant company. We did a project together with Total to investigate the effect of anti-foaming agents in oil, and we compare different kinds of lubricants in terms of tendency to produce or to reduce foam generation. I will show you very preliminary results. The activity is actually completed. We are working on a full paper that will be presented, submitted, and presented at our conference in October. The conference will be in Munich, in Germany. So I show you some results to give you an idea of what was done. The cooperation with Total Energy dates back to 2019, and what you see here is another paper that was presented by Total Energy in our conference in 2021. This is related to electric motor cooling simulation, so a totally different topic, but this is just to tell you that Particleworks and Total cooperated on different topics related to lubricant foaming, lubrication of gearboxes, and also cooling of electric motors to support the development of new fluids. What we did together with Total was a two-step process. The first step was to simulate a very simple single gear gearbox that you see here, and we simulated different levels of RPM, low, medium, high RPM, to tune our foaming model for different kinds of fluids. So starting from available experimental data from the Total Energy laboratory, what we did was to tune the parameters of the foaming model to be able to capture the bubble size distribution and the foam volume fraction in the oil for different kinds of lubricants. Starting from the available data, we were able to validate for 1 RPM and then to verify the consistency of the model for different RPM. And the model, after the original validation on 1 RPM, was able to show good accuracy also for lower and higher RPM. Here you see, for example, the effect in terms of visual effects in terms of height of the foam layer, and you cannot see the bubble size distribution. This is something that we will share with the complete and full paper in October. After the original validation, after the initial validation of the model, based on a single gear and based on different lubricants, we started using a more complex, a standard, but a more complex gearbox with the 2 gears to start simulating real conditions. Again, we used the same hardware, 2 kinds of lubricants, different lubricants, and we simulated a wide range of RPMs to again compare the different lubricants and to compare the effects of different RPM. The hardware, so the gearbox, was the same. So in that case, the 2 parameters were the effect of the rotational speed and the effect of the lubricant. And the software was able to show the same trend between the two lubricants. So lubricant A compared with lubricant B, we had not only the same trend, but also the same amount of foam, the same amount of um, ratio, the same ratio between the two lubricants. That was measured at the test bench. So starting from the original validation, we were able to extrapolate and use the model for other cases, for real hardware and for real operating conditions at different RPMs. Here you see the video where you see not only the foam generation, but also the foam distribution and transportation. And again, all the results will be available soon. Similarly, the same model after talking about gearboxes, we can show some couple of examples related to um, oil sump and air entrainment at the pump, at the engine pump. Here you see how the how the bubble transportation is calculated in the system, and its and the effect of um, specific designs of the air inlet section can be designed and simulated to minimize the air entrainment. The same model can be used in dynamic conditions, so static and dynamic conditions. So not only uh, bubble generation due to the air entrainment, starting from clean and pure oil, but also air entrainment associated with dynamic condition. So in this case, the pump is not only aerated, or let's say the problem is not only related to the presence of bubbles in the lubricant, but also to the oil level, reduction of the oil level at the pump due to the um, to the tilting of the engine. Both phenomena can be included in the same simulation, in the same kind of simulation. Conclusions. As we said, lubrication and cooling associated to gearboxes, electric motors, pistons, engine sump can be affected by foaming. Foaming has different effects in terms of efficiency, increase of power losses, reduction of performances of pumps and gearboxes, and also in terms of reliability and life of engines and gearboxes, especially at high speed, when the mechanical effects of air entrainment, but also of cavitation and air release from the oil can be relevant. Um, Particleworks and Prometech developed a specific model um, to be able to predict at least the mechanical effects, at least the mechanical phenomena that produce air entrainment and foam generation in lubricants. This kind of model is available from the standard Particleworks software. It can benefit from the meshless CFD methodology. It can benefit from GPU acceleration to speed up the simulation process. What the software can calculate is bubble generation, transportation, lifetime, and foam characteristics, mainly bubble size distribution and volume fraction. The software can be used also to compare different lubricants. In this case, since the software cannot account for the chemical effects, a tuning of the specific lubricant, of the model for the specific lubricant, must be done. So experimental data are needed to characterize the lubricant, but this is only needed when you need to compare different lubricants. This is not needed when you want to compare different operating conditions or different hardware, different designs. And this is the main use of the software and model, to be able to analyze different designs virtually, optimize the system and the design to minimize foaming, and so minimize the drawbacks of foaming. And at the end of the day, to produce reliable and more efficient gearboxes and engines. Um, Unfortunately, we were not able to show all the details of the activity we recently completed with Total Energy, but Total Energy will be at the next Particleworks experience in October in Munich. So I invite you to join us in the conference in Munich. You can visit our website and you will find all the details soon on our webpage. Thank you for attending, and if you have any questions, please let me know.